check. Online ළමයින්ට පැහැදිලි වෙනවද කියලා confirm කරන්න. Online students, can you hear me clearly? Online students, can you hear me clearly? Online students, can you hear me clearly? Students in the YouTube live and the Zoom webinar, please confirm whether you can hear me clearly. So now we have to so let's start then. Okay, so today like we are actually like, you may think what is the reason to like discuss some random topics. No, these are not actually random topics. We have already done, you for English medium students, we have already done 3 seminars, one for current electricity and electricity power, and the other one is electromagnetics, and other one was electronics. This is the next one, and more seminars are coming. Today night also you have a seminar for optics and waves. We'll explain everything with demonstrations for optics and waves, which would be much convenient because many students don't understand things because you haven't seen the demonstrations of optics and waves. So if you see the demonstrations properly, you will have a very nice idea. So now we are going to discuss few areas of the mechanics part. Mechanics in the sense work, power, energy, equilibrium, and hydrostatics. We are going to discuss these areas. Okay, we are going to discuss these areas now. Okay, so the thing is, okay, so the thing is, our plan is for now is to cover these areas such that you have a very solid understanding in theory, so that you won't struggle in mainly in theory and some calculation related questions. Okay, so more sessions are coming. Even in this Monday we are planning to do few more sessions, but it is entirely based on what you ask. So when you are just in the session, just put some messages on the Zoom chat, put some messages in the YouTube live chat what you find difficult, especially in the physics area of science. Okay, and our short notebook and the answer scripts are provided in the groups, and it will be again provided in the Zoom chat. It will be again provided in the Zoom chat and in the YouTube live chat. You can refer to them. It contains the entire physics syllabus with the answer script too, and also it contains nice questions and a short note too. Okay, so let's start with the session. And I'm Jandulilanand, an electronics engineer and a A-level physics tutor. So you will see me again if you are learning if you are doing bio or maths for A levels, but it's a different story. For now, let's focus on O levels. Okay, so let's start with the session. I'll start with the equilibrium part, then I'll move to work, power, energy, and hydrostatics part. I'm going to discuss the most important parts and some certain stuff beyond A levels, so that, I mean, when you learn a bit beyond O levels, you can understand things in O levels better. Okay, so let's do it that way. So let's start the session. So electromagnetism is hard. I have already, there's a message that electromagnetism is hard. We have already done a seminar for electromagnetics. Okay, I'll provide that in the group. We will create a channel. You can use that channel to get all the past recordings and all the tunes and all. Okay, so let's start. So what is equilibrium? Equilibrium in the sense something is staying stationary or moving at a constant velocity. That means something doesn't have any resultant force or any resultant moment, then we call it in equilibrium. That means if there is an object, okay, if no forces act on this object, if no resultant force act on this object, okay, if there is no resultant force acting on this object, and if there is no resultant torque acting on this object. Torque in the sense the moment. We know that if there is a force, an object will try to move. Clear? If there is a force, an object will try to move. Clear? So to stop the movement, to stop the linear motion, there shouldn't be any resultant force. Okay. So one part of an equilibrium is there shouldn't be any resultant force on the system. And the other part of any equilibrium is that there shouldn't be any rotation on the system. So how could we avoid a rotation? There shouldn't be any moment. There shouldn't be any moment, right? We know that the moment of a force Fr, there shouldn't be any moment. So if there is no moment, system will not rotate. If there is no force, system will not move. Then that is in equilibrium. Okay, then that is in equilibrium. That's the basic outline of equilibrium. Okay, so talking about this, we will first talk about the equilibrium under two forces. Okay, we'll first talk about the equilibrium under two forces. Okay, so here if we take an object like this, there will be a, if you hang an object like this, the object will stay stationary, right? The object will be in equilibrium. What is the reason? Because there are two forces acting on the system. One is the weight, another one is the tension by the string. Something that you should see is if you just place it like this, it won't stay like that, right? It won't stay like that. If you place the ball like this, it won't stay like that. It will fail, right? It will fail such that it looks like this. It will fail such that it looks like this. Why? The reason is for equilibrium under two forces. T and mg. For equilibrium under two forces, the forces should be in the same line. Forces should be in the same line of action. So these two must be in the same line for the system to be in equilibrium. Okay. And the other requirements are these two should be equal in magnitude. That means T should be equal to mg and they should be in opposite direction. Okay. It's understandable, right? If two forces are not in the same line, if I provide two forces, see, this will rotate. Only if they are in the same line, it will not move. Clear? Only if they are in the same line, it will not move. Clear? So for equilibrium under two forces, the requirements are the forces should be equal. Clear? For equilibrium under two forces, the forces should be equal. Clear? And the other one is forces should be equal, and the other one is they should be in opposite direction. And the other one is they should be in the same line of action. Clear? So this is the story. Next. What is mg? Here mg is the weight of the object. Using mg, I'm just mentioning the weight of the object. Weight, mass into gravitational acceleration, mg, the weight. Tension is the tension in the string. Clear? Just two random forces I took as the example. And there's another question. What is F and what is R? What is F and what is R? What is F and what is R? F සහ R කියන්නේ මොකක්ද? F is the force, R is the distance to that force. Can you remember? Moment. F is the force and R is the distance to that force. F කියන්නේ බලය, R කියන්නේ ඒ බලයට තියෙන දුර. Clear? F is the force, R is the distance to that force. Okay. So just let me know if you need me I mean, even English medium students, just let me know if you need me to explain some stuff in Sinhala too, okay? Even in A levels, I do 2 classes, an entirely English medium class and another one English Sinhala mixed class, because even English medium students sometimes understand better when we explain some stuff in Sinhala, okay? සමහරලාට සිංහලනොත් කිව්වම තමයි English medium ළමයින්ටත් හොඳට තේරෙන්නේ. ඒකින්ද A level වලත් අපි English fullම English එකකුයි සිංහල English mix එකකුයි දෙකක් කරනවා. අර ඒක තමයි ඒකේ හැටි. ඒකින්ද අර එහෙම අවශ්‍යතාවයක් තියෙනවා නම් කියන්න අනිවාර්යෙන්. හරිද? Okay, so moving forward. So this is just an example, okay? This is just an example. That means the tension and the weight. Weight is the weight of the object. Tension is the tension by the string. If they are in the same line, okay, they should be in the same line. They should be equal in magnitude. They should be in opposite direction. They should be in opposite direction. So the story is, for equilibrium under two forces, these two forces should be equal in magnitude. Should be equal in magnitude. They should be in opposite direction. And they should be in the same line. Okay? And they should be in the same line. Clear? So that is the idea. Okay? Got it? Up to this point? Okay? Did you understand up to this point? මෙතෙන් වෙනකම් පැහැදිලිද කට්ටියට? බල දෙකක් යටතේ පද්ධතියක් සමතුලිත වෙන්න නම් මොකද්ද වෙන්න ඕනේ? ඒ බල දෙක විශාලත්වයෙන් සමාන වෙන්න ඕනේ, දිශාවෙන් ප්‍රතිවිරුද්ධ වෙන්න ඕනේ, එකම ක්‍රියා රේඛාවේ තියෙන්න ඕනේ. පැහැදිලිද? විශාලත්වයෙන් සමාන වෙන්න ඕනේ, දිශාවෙන් ප්‍රතිවිරුද්ධ වෙන්න ඕනේ, එකම ක්‍රියා රේඛාවේ. එකම ලයින් එකේ තියෙන්න ඕනේ පද්ධතිය. පැහැදිලිද? හරි. අපි ඉස්සරහට යමු. Okay. So the next one. Next one. So after this point, okay, after this point, this is the simplest version, okay. This is the simplest version of an equilibrium, okay. Equilibrium under two forces. බල දෙකක් යටතේ සමතුලිතතාවය. මේක තමයි අර සමතුලිතතාවයේ තියෙන පුළුවන් සරලම ආකාරය. පැහැදිලිද? The simplest version of equilibrium. Then the next one. The next one. Now equilibrium under three forces. Okay. Equilibrium under three forces. බල තුනක් යටතේ සමතුලිතතාවය ගැන කතා කරමු. What is equilibrium under three forces? That means if we take a system like this, okay. Again, let's take a example. There's a weight. So in your book, usually they use W for the weight. So this mg I used, this mg I used, it is actually weight, right? Okay, it is actually weight. I think you have seen this mainly in your book as W, right? Okay. So sometimes if there's a weight like this, we sometimes balance things using two hinges like this, right? අපි සමහරවිට මෙහෙම ආධාරක දෙකකින් පද්ධතියක් balance කරනවානේ. We sometimes balance the system using two hinges like this. So this is equilibrium under three forces. One is W, and these two hinges create two upward forces, okay? These two hinges create two upward forces. Clear? So this is equilibrium under three forces, okay? This is equilibrium under three forces. So what is the requirement for this system to be in equilibrium? මේ දෙන්නගේ සමතුලිතතාවයට තියෙන අවශ්‍යතාවය මොකක්ද? The requirement is these two forces should balance this guy. බල දෙකක් එකතු වෙලා තුන්වෙනියව බැලන්ස් කරන්න ඕනේ. That means resultant of F1 and F2, the sum of F1 and F2 is F1 plus F2. This F1 plus F2, this F1 plus F2 should be balanced by W. Clear? This F1 plus F2 should be balanced by W. Clear? F1 plus F2 equals W. Clear? F1 plus F2 equals W. So the weight should be balanced by F1 plus F2. Clear? So the next one. It's actually the equilibrium under three forces, but the forces are parallel. Okay? But the forces are parallel. So the actual story is there are two forces, F1, F2. I simplify and a third force W. What actually happens is I simplify this into two forces. How? I add these two. When I add them, I get F1 plus F2, right? When I add them, I get F1 plus F2. Clear? And it should be equal to W. It should be equal to W for the system to be in equilibrium. Clear? It should be equal to W for the system to be in equilibrium. Clear? So F1 plus F2 should be equal to W. Clear? So the next one. This is equilibrium under three forces, but when the system is when the forces are parallel. Clear? Equilibrium under three forces when the forces are parallel. Clear? Then what about equilibrium under three forces when the systems are not parallel? What about the equilibrium under three forces when the system is when the forces are not parallel? For an example, let's take this from your textbook. A photo frame hanged using two strings. So this is made out of three forces, right? This system is made out of three forces. What are the three forces? One is T1 going like this. Another one is this T2, and the other one is the weight. Okay, and the other one is the weight. So these are the three forces acting on the system. These are the three forces acting on the system. So if these are the three forces acting on the system, for them to be in equilibrium, what are the conditions? There's one fundamental condition. It is they should meet at the same point. Why? Why should they meet at the same point? Let's take a simple example. There's an object like this. Okay. There are two forces like this. Let's assume F1 and F2. And I need to bring the third force to balance the system. So the simple idea is I can get the resultant of these two forces. So when I add these two forces, they will act as one single force, right? They will act as one single force, F1 plus F2. When I add these two forces, they will act as one single force. And the third force should balance them out. Okay? Third force should balance them out. So for this to happen, all these three forces should meet at the same point. Clear? For this to happen, all the three forces should meet at the same point. So if a system is under equilibrium under three forces that are not parallel, all of them should meet at the same point. Clear? All of them should definitely meet at the same point, and the resultant of two forces should balance the third force. Clear? Resultant of two forces should balance the third force. So F1 plus F2 should be balanced with F3. Clear? F1 plus F2 should be balanced with F3. Clear? So that is the idea. So that is the idea. That is the idea for equilibrium under three forces. Okay. That is the idea of the equilibrium under 3 forces. And like you should understand, when it is equilibrium under 3 forces, it actually simplifies up to equilibrium under 2 forces, right? How I explain things is, මම කොහොමද දේවල් පැහැදිලි කරන්නේ? Even when it is 3 forces, what I first do is I add 2 forces and make 2 forces a 1 force. Clear? I simplify 2 forces into 1 force. Okay? බල දෙකක් මම මුලින් එකක් බවට පත් කරනවා. Then the requirement is it should balance the third force. Okay? Clear? Then the requirement is it should balance the third force. Okay? So that is equilibrium under 3 forces. The resultant of 2 forces should be balanced with the third force. Clear? Resultant of 2 forces should be balanced with the third force. That's all. Clear? That's how the equilibrium under 3 forces works. That's how the equilibrium under 4 forces work. Okay? How? You can simplify it up to 2 forces, then do the calculations. That means assume, for an example, assume that there is a system like this. There is a system like this: 5 newtons, 4 newtons, 3 newtons, and a force F. What should be F? What should be F for the equilibrium? What should be the value of F for the equilibrium? What should be the value of F for the equilibrium? What should be the value of F for the equilibrium? It should be 6, right? Why? At the end of the day, you can think this as 2 forces. 5 plus 4 becomes 9. 5 plus 4 becomes 9. And in this direction, you have F plus 3. In this direction, you should have F plus 3. Okay? So 9 should be equal to F plus 3, right? For the equilibrium under 2 forces. For the equilibrium under 2 forces, this resultant should be equal to this resultant. That means these 2 forces. Now it's not 4 forces. I added the forces in the same direction. Okay? Then I have altogether 9 here. And I have altogether F plus 3 here. These 2 should be equal. That's the story, right? These 2 should be equal. That means F plus 3 should be equal to 9. That means F should be 6 newtons. Okay? F should be 6 newtons. And there was a question. What is the meaning of coplanar? There was a question. What is the meaning of coplanar? Coplanar means, in many of these questions we discuss about forces in the same plane. Forces in the same plane. That means take this whiteboard as a plane. All these forces are on this plane. So these equilibrium laws that I learned, they works for forces in the same plane. Because now think, now I'm applying a force upward and I'm applying a force downwards. So see, it's balanced. Object is not moving, it's balanced. Object is not moving, it's balanced. Why? If you look from side, object is balanced. Why? See, they are in the same plane. These forces are in the same plane. But see, that means just like this whiteboard, they are in the same plane. But think, if one force is out of the plane, like this. Now see, this force is in this plane. This force is in this plane. This force is in this plane. See, 2 planes. This force is in this plane. And this force is in this plane. Now what happens? Now if I apply the same forces, see, object will rotate. See, object will try to rotate. See, because the forces are not on the same plane. See, this is one plane and this is another plane. Clear? If I show it like this, see, now forces are in the same plane. These are coplanar forces. See, so these explanations work for coplanar forces. But if, see, now this force is in this plane, this force is in this plane. Now if I apply a force, see, it tends to rotate. See, it tends to rotate. See, that is the meaning of coplanar. Clear? So these laws that we learned, okay, these laws that we learned actually works for coplanar forces. ඒක තල බල. එකම තලයේ තියෙන බලවලට තමයි මම මේ කිව්ව කතන්දර ගොඩක් වළංගු වෙන්නේ. පැහැදිලිද? All of these laws works for the forces in the same plane. Clear? All of them works for the forces in the same plane. Forces are that forces that are on the same plane. Clear? That is the idea. Let me know. Is it clear? Yeah. So like so what is there's a question, what is tension? What is tension? Tension is a force that appears in a string, okay? Tension is a force that appears in a string. These are just forces. I gave just different names for them. There are standard names for forces. A force that appears in a string, we call that tension. The weight or mg is the gravitational force on an object. Weight or mg is the gravitational force on an object. Clear? So these are just names given for these forces. At the end of the day, tension is a force. It is the force given by a string. Weight or mg is a force. It is the force created by the gravitational pull on an object. Clear? So that is the idea. So if I ask you a random question, why if you place something on a table, it is under equilibrium? Under how many forces? If you place something on a table, if you place an object on a table, under how many forces is it under equilibrium? Under how many forces is it under equilibrium? It's under two forces. What are the forces? You should be able to figure out the two forces. What are the forces? One is the weight of the object, W, or mg. Weight of the object, W. Another one is the reaction from the table. The table is creating an upward reaction, right? Here, the table is creating an upward reaction. So this is in equilibrium under these two forces. And for this system to be in equilibrium, these two forces should be equal. So R should be equal to W, and they should be opposite. R equals W. They should be opposite, and they should be in the same line of action. Okay, and they should be in the same line of action. That is the idea. Okay. Should be in the same line of action. That's how it works. There was a request like to do more questions. Yes, I'm planning actually to maybe most probably on Monday I'm planning to do a full full revision of the syllabus with some questions. Okay, I'll let you know about that in the group. So there's a Monday related plan to like cover a huge area of the syllabus with a lot of questions and all. I'll let you know about that. Okay. Next. Moving forward, um, the other part that a lot of students asked was the hydrostatics part. That's all. Okay, in the all level syllabus, that's all you have about equilibrium. Okay, we don't talk about rotation or anything. Okay, we don't talk about rotation or anything. What we talk about is linear forces. Okay, but just remember, I mean, in all these explanations, I said that they should be in the same line of action. Okay, for equilibrium under two forces, I said that they should be in the same line. Why? Otherwise, it will rotate. Think about a pen like this, and if I apply two forces like this, it will not move. If I place a pen like this and if I apply two forces, it will not move. But if I have the pen like this, and if they are not in the same line, if these two forces are not in the same line, what happens? If these two forces are not in the same line, what happens is, see, it tends to rotate. When I apply two forces, it tends to rotate. So they should be in the same line of action. Clear? They should be in the same line of action and they should be in the same plane too. Okay, there are much more complex requirements. Same line of action and the same plane. Clear? That is the requirement for an equilibrium. Clear? That's the requirement for an equilibrium. So let's move forward. Hydrostatic pressure and its applications. Hydrostatic pressure and its application. So don't worry, I'm planning to go with a question round, most probably on Monday, covering a huge area. Okay. So okay. Now moving forward, pressure. What is pressure? What is the basic definition of pressure? Write it in the chat. What is the basic definition of pressure? පීඩනය කියන්නේ මොකක්ද? පීඩනය කියන්නේ definition of pressure is if we apply a certain force on an area, okay, pressure is defined by that force. Actually, that force should be perpendicular, okay, that force over area here, that force over area. So the pressure is defined as force over area, F over A. Clear? Pressure is defined as force over area. That means the force applied on unit area. ඒකක වර්ගඵලයක් මත ඇතිවන බලය. So this is measured in newtons. Area means meter squared. So we get what? Newton per meter squared. Newton per meter squared means pascals. Clear? Newton per meter squared means pascals. Okay. So that is the idea. Okay. Now, talking about this pressure, hydrostatic pressure means the pressure created by a liquid, okay? A stationary liquid. Hydrostatic pressure is the pressure created by a stationary liquid. Okay. So, now, if there is a liquid in a bottle or somewhere, if you take a certain point, there's a lot of water. If there's a lot of water like this, all this part of water, all this water has a certain weight. All this water has a certain weight. Clear? All this water has a certain weight. Okay. They create a certain weight downwards. Clear? They create a certain weight downwards. Now, this weight of this water is felt here. This weight of this water is felt here. So this weight actually acts as a force, right? In this case, the force acting on this surface is the weight of the water, right? Force acting on this surface is the weight of the water. And the pressure on this surface can be written as force over area, which means the weight over area. Okay. That is hydrostatic pressure. Pressure created by the weight of liquids. Clear? Pressure created by the weight of liquids. Okay. So, I can actually find an equation for this. If the height of this water is h, if the area of this water is A, what is the volume of this water? What is the volume of this water? What is the volume of this water? It is area into length. Right? Area into length gives me the volume of water. Now, if I get the mass of this water, okay, I can write it using the definition of density. Tell me the definition of density, people. What is the definition of density? What is density? ඝනත්වය කියන්නේ මොකක්ද? What is density? Okay. Density is mass over volume, right? Density is mass over volume. So in this case, this is mass. Volume is AH. Volume is AH. Here, volume is AH. Then I get the mass as AH. I cross multiply. I take AH here. Then I get AH rho. Then I get AH rho. Then how do we get the weight by mass? How do we get the weight using mass? Tell me. How do we get the weight using mass? We multiply mass by what? Yes. We multiply the mass by the gravity. We take mass and multiply it by G, gravity. Then we get the weight. So here we get AH rho. Mass is AH rho. Then here I have G. So now I can write here weight is AH rho G divided by area, which is A. So it is AH rho G over A. Then what happens is area cancels out. Then I get H rho G. Clear? Then I get H rho G. So this is the equation for the hydrostatic pressure. That means if there's certain water column, and if the height of that water column is H, the pressure at this level is H rho G. Then what is the pressure here? If the height is H1, what is the pressure here? Pressure here becomes, then height is H1, so it becomes H1 rho G. Here, pressure here becomes H1 rho G. So it responds to the height. Clear? Pressure is a function of height. Clear? Pressure is always a function of height. And please remember, it never depends on the shape of the water column. Okay? It never depends on the shape of the water column, which means so rho is density. Okay? Rho is the symbol I use for density. Okay? Rho is the symbol I use for density. Okay? T is pressure. Rho is the symbol I use for density. I mean, I'm using the standard notations. Okay? These notations are in your textbook. Okay? So you should know them. Okay? The notations are just exactly similar to what you have in your textbook. Okay? Okay. Now, moving forward. Okay. Moving forward. Please remember that this pressure never depends on the shape of the water column. Okay. That means even when the shape of the water column is like this. Even when the shape of the water column is like this. Even when the shape of the water column is like this. If the height is same as H, pressure here, and pressure here, all three is equal to H rho G. Okay? All three is equal to H rho G. Pressure in all three cases is equal to H rho G. Clear? Pressure in all these three cases is same as H rho G. Okay? So that is the equation for the pressure. Okay? So you have to remember, at a certain height, okay? At a certain height, you have the same pressure no matter what is the shape of the system. Clear? At the same height, you have the same pressure no matter what is the shape of the system. Clear? And at the same time, at a certain height, you have the same pressure on all the directions. Okay? you have the same pressure on all the directions. Clear? That means in this direction, in this direction, in this direction, this direction, and this direction. On all directions, you have the same pressure, okay? Even in these directions. So in all the directions, you have the same pressure H rho G, okay? Same pressure H rho G. There was a question, pressure is a vector or a scalar. It's actually a scalar. Why? See here, I can't specifically design what is the direction of the pressure here. It acts in all the direction and it's similar in all the direction. Clear? It acts in all the direction and it's similar in all the directions. Clear? So I can't specifically tell that pressure is in this direction or pressure is in this direction or pressure is in this direction. I can't specifically tell. See? I can't specifically tell the direction. So I can't define a proper direction for the pressure. So it can't be a vector in this case. Clear? I can't under this scenario, I can't specifically decide the direction of this hydrostatics pressure. So we consider it as a scalar. Clear? But the idea, these are the properties of pressure. Okay, these are the properties of pressure. Okay. Okay, let's move forward. Okay, let's move forward. Let's move forward. So this is the behavior of pressure. Okay, there are more requirements about the pressure. Okay, there are like more stories about pressure, things like pressure at, I mean, if I conclude things, okay, if I summarize things, at the same height you have the same pressure. Okay, and at a certain height it only depends on the height, not on the shape of the system. Okay, and pressure is same in all the directions at a certain point. Okay, you can't specifically tell which this is the direction of pressure or this is the direction of pressure. At this point you have the pressure in all the directions. And again, yeah, these are the main factors, and pressure is written using P equals H rho G. Okay, pressure is written using P equals H rho G. And there are multiple benefits of this pressure. Okay, there are multiple benefits of this pressure. One of the main benefits of this pressure is pressure transmission devices. Pressure transmission devices. What are pressure transmission devices? Pressure transmission devices are like this. Have you seen these hydraulic jacks? Have you seen these hydraulic jacks? Actually, like, pressure is not always useful. Okay, can you remember these days? What happens? Lot of floods, lot of landslides. Nayayam gangwatura katandara godak tibbane. Lot of floods and landslides in certain areas. In certain areas, very strange thing happened. Okay, since these things happened recently, they may ask these things. Okay, very strange things happened in certain areas. That was, there's a land and a landslide happens here. They may ask, they may give this as an example and ask you what is the reason for this. Okay, there is some water body here, a small lake or something like that, a small lake or something like that. Now a landslide happens. A landslide happens. Okay, a huge landslide happens. Now this is just a road or a huge land. And few kilometers away, or few meters away, or few 100 meters away, there's a village here. There's a village here. All of a sudden, due to this landslide, all of a sudden, due to this landslide, this village gets flooded. This village gets flooded due to this landslide. What is the reason? What may be the reason? Tell me, what may be the reason? Landslide happens here. All of a sudden, flooding happens here. What may be the reason for this? What may be the reason for this? Someone? Someone? Any idea? No, it's not the pressure acting on the land. What actually happens is some areas, okay? Some areas, although they looks like land, okay? In some areas, although they looks like lands, it's actually a huge water body around. Okay? It's actually a huge water body around. Here. Although it's land, there's a lot of water underneath, and these areas are connected by this water body, okay? These areas are connected by these water bodies. Now what happens is, okay? Now what happens is when this landslide happens into this water body, it creates a certain pressure on this water body, and that pressure is transmitted through the liquid up to this point. So all of a sudden pressure increases. All of a sudden pressure increases. So all of a sudden due to this increased pressure, water goes up. Water goes up. Just like a hydraulic jack. In a hydraulic jack, what happens? There's a jack like this. Okay. If we apply a force on this system, okay. If we apply a force on this system, this one goes down. This one goes down, then this one goes up here. Then this one goes up. If we apply a force here, this one goes down, then this one goes up here. That's what happens, okay? That's what happens. Clear? Got the idea? Did you understand it? This kind of practical stuff you should have a good understanding due to recent activities and all, okay? So the story of a hydraulic jack is that, okay? That's the same thing happens in a hydraulic jack. That means we have a vehicle here. We need to lift this vehicle. So for that we apply a force here. Now what's mentioned by the pressure transmission law? What is mentioned by the transmission of pressure? Since liquids do not compress, when we apply a certain pressure here, the same pressure is transmitted until here through the liquid. Same pressure is transmitted until here through the same liquid. Clear? So that means if the force here is F, let's call it F1. If the area here is A1, pressure felt here, P is F1 over A1. Pressure felt here is F1 over A1. Clear? And at the same time, okay, and at the same time, the same pressure is transmitted through the liquid and felt on this piston. So due to this pressure on this piston, a force is created on the piston. How can I get that force? I'll call that F2 and area A2. Since it is the same pressure exerting here, it also can be written as the same pressure P, and it is equal to F2 over A2, force over area. It can be written as F2 over A2. Since it is the same pressure that gets transmitted from here to here, F1 over A1 equals F2 over A2. F1 over A1 equals F2 over A2. Then we can write what is F2? What is F2? F2 is F1 A2 over A1. Clear? F1 A2 over A1. So I can get F2 using the relationship between the areas. Okay, using the relationship between the areas. So for an example, if it is a hydraulic jack, if I apply 100 newtons on an area of 5 centimeters squared, and if this area is 100 centimeters squared, how much of a force will be applied on this vehicle? I can write the pressure is same in both points. So 100 over 5 centimeters squared should be equal to F over 100 centimeters squared. Clear? 100 force over area 5 centimeters squared here equals to force F over area 100 centimeters squared. Then I'm gonna get what? Then I'm gonna get here 100 over 5, cross multiply and bring this 100 here. Then I'm gonna get what? 20 into 100. 20 into 100. Clear? Which means 2000 newtons. Clear? 2000 newtons. Clear? And a force of 2000 newton acts here. So this can be used to amplify the force. Did you see? I just applied 100 newtons because I can't lift a vehicle alone, right? I can't lift a vehicle alone. I don't have enough strength. Okay, I can't provide 1000 newtons as a human, but using a hydraulic mechanism, I can apply 100 newtons and produce 2000 newtons here. Clear? I can apply 100 newtons and produce 2000 newtons here. Clear? So that's the functionality of a hydraulic jack. Clear? That's the functionality of a hydraulic jack. Okay. So moving forward, is it clear up to this point, everyone? Same kind of mechanisms are used in brake system in a vehicle. Okay, same kind of mechanism is used in brake mechanisms in a vehicle. That means what usually happens is you have a full hydraulic system like this. Full hydraulic system like this. We have a full hydraulic system like this. This is the pedal. You apply a certain force here. Then the liquid gets pushed. That pressure is transmitted here, and the same pressure is transmitted here, and it is connected to two plates like this. And you have the wheel of the vehicle here. Now what gets happened is this pressure will be transmitted here, so they will be pressed against this. Okay, they will be pressed against the tire. So the tire will stop. Okay, so the tire will stop. So this is the mechanism of a hydraulic system. Okay, this is the mechanism of a hydraulic brake system. Okay, hydraulic brake system. Same liquid pressure continues to all the areas. Clear? Same liquid pressure continues to all the areas. Clear? Clear? Got the idea? Okay, moving forward. Just put, if you have any questions, put them in the chat. If you have any questions, put them in the chat. Okay, I checked the questions you mentioned in the YouTube live chat too. Yes, there was a request to do hydrostatics pressure. Sorry, gas pressure, atmospheric pressure. I'll discuss that part too. Okay, so this is hydraulic pressure. Okay, pressure created by uh, hydrostatic pressure. Okay, so moving forward, a gas produce a similar pressure. Okay, any gas produces similar pressure. That means take our atmosphere. We in Earth, on Earth, above Earth, we have a huge atmosphere. Okay, above Earth, we have what? A huge atmosphere. Clear? We have a huge atmosphere above Earth. Now, this air column above us, if there's a person here, this huge air column above us is entirely similar to a liquid column in this scenario, right? It's just like a liquid column in this scenario, right? So this huge air column will definitely create a weight. This huge air column will definitely create a weight. So due to that weight, this person will definitely feel the pressure, okay? Due to that weight, this person will definitely feel the pressure, okay? This is one type of pressure that gas can produce, okay? Just the atmosphere kind of pressure, okay? නිකන් වායුගෝලයෙන් ඇති වෙන පීඩනය due to the weight of the gas. So it's just equal to the normal liquid pressure. But you have seen another type of pressure. Take a balloon. What happens in a balloon? When you pump air into a balloon, it expands like this, right? When you pump air into a balloon, it expands like this. Why? What is the mechanism of pumping? What is the mechanism of pumping air into a system? When you pump air into this system, what you do is you just compress them. That means gas particles likes to stay at a certain distance. They don't like to stay very close to each other. If you try to bring them really close to each other, they will repel each other. They will push each other away. Clear? They will push each other away. Clear? They will repel each other and they will push each other away. Clear? So if they push each other away due to this attempt to push, so there's a lot of liquid, lot of gas in this. Okay, I have compressed them into the balloon. They try to push each other. They try to push each other away. Clear? They try to push each other away. When we try to push each other away, what happens? The balloon feels a pressure like this, right? A balloon feels a pressure like this. Clear? The balloon feels a pressure like this. That means it gets this compressed gas, compressed air try to expand. They like to expand and stay at their standard distance. When they try to expand, they create another pressure. That is another way that gas can create pressures. Okay. So gas create a pressure using two mechanisms. One using its weight, one using its own weight, the huge weight it has. Okay, and the other by the attempt to expand. Clear? By the attempt to expand. So when we are talking about any kind of a pressure, we have these two components. Okay, but when it comes to atmospheric pressure, normal atmosphere, it is not actually compressed, right? Normal atmospheric pressure that we feel, it is not actually compressed. So it usually don't have this type of a pressure. Usual atmosphere have this type of a pressure. Okay. Okay. That's what we feel as the atmospheric pressure around us. Okay. That's what we feel as the atmospheric pressure around us. And there are mechanisms to measure this atmospheric pressure, right? Okay. Actually, there are more, like we can measure the atmospheric pressure like this. How? What we do is we take a mercury column. That means we take a tube and put a lot of mercury into that. We take a tube and put a lot of mercury into that. Okay. Now what we do is we put this mercury tube into a mercury tub. Since it was entirely filled, now the mercury will go down a bit and it will create a vacuum here. It will create a vacuum here. The best thing about a vacuum is it don't create a pressure. Why? In a vacuum it doesn't have particles, right? In a vacuum it doesn't have particles, gas particles, so it can't create a pressure without a gas. So there is no pressure here. So the pressure here becomes H rho g, right? Pressure here becomes H rho g. Clear? If the height is H, pressure here becomes H rho g. And the best thing is we know that in a liquid pressure is equal at the same level, right? In a liquid pressure is equal at the same level. So if this if the pressure here is H rho g, pressure here is also H rho g, and the best thing is this point is in contact with atmosphere. So this place feels the atmospheric pressure too. Clear? So this same point from this side it feels the atmospheric pressure. Through the liquid it feels H rho g. So using this mechanism we can write the atmospheric pressure using H rho g, right? The same pressure here, when you calculate using the mercury column from this side, it is H rho g. When you calculate from outside, it's just in contact with the atmosphere. So the pressure here it is just the atmospheric pressure. So here atmospheric pressure P naught equals H rho g. Clear? Atmospheric pressure P naught equals H rho g. Here, that's how we get the answer. Okay, that's how we get the answer. Clear? Got the idea? Got the idea? So this is, we call this the barometer. This is mercury barometer. We use mercury, the pressure created by a mercury height, to measure the pressure. There are some other ways too, okay? There are some other ways too. There are mechanical barometers. Mechanical barometers usually use a balloon like this, a small balloon type structure, and it is open to the atmosphere. So due to the atmosphere, this balloon will feel a certain pressure, and due to the based on the expansion of this balloon, it rotates a lever. It rotates a lever and show you the pressure. Okay, it rotates a lever and show you a pressure. So these are mechanical barometers. It uses the expansion of a diaphragm. It's used the expansion of a diaphragm. යම් කිසි අර මොකක් හරි balloon එකක් වගේ එකක ප්‍රසාරණය වීමට දරන උත්සාහය. It used the expansion of a diaphragm to measure the pressure. Okay, it used the expansion of a diaphragm. Okay, so that is the story about atmospheric pressure. Okay, and if anyone needs the tune, need the previous recordings, need to join the groups, or need any information other than, need any support after all levels, any for anything, then contact our hotline. Okay, 070-154-6825, 070-154-6825, 070-154-6825. Okay, there are many other applications of hydrostatic pressure. Okay, there are many other applications of hydrostatic pressure, like what? We can see multiple applications. One is that you have seen these kind of things like rubber suckers that we use. That means, have you seen, there are hangers, small hangers, that when you press it against the wall, it stays there, right? And you can hang something here. Okay. So what is the mechanism of this? So it comes like a cup like this. You place it here and you press it. When you press it, what happens? All the gas inside that goes out. When you press it, all the gas inside that goes out. Here, all the gas inside that goes out. Here, when all the gas sucks out, when all the gas goes out, this part becomes almost like an vacuum. Okay, this part becomes a vacuum. No air inside this. Clear? No air inside this. This part becomes a vacuum. Now when this part becomes a vacuum, okay, now when this part becomes a vacuum, what happens? When this part becomes a vacuum, external pressure applies on this, right? External pressure is there, the atmospheric pressure, the external pressure is there here, and there's a vacuum inside. So the pressure difference holds the system. Clear? The pressure difference holds the system. Clear? Pressure difference holds the system. Okay, it won't let this go. That's the mechanism. Okay, that's the mechanism. Pressure holds the system. Clear? Okay, there are multiple other examples like this. Okay, just for an example, a simple example is the straw, right? What happens in a straw? Here you have the atmospheric pressure. Here also you have the atmospheric pressure, and there's a small height. So here the pressure would be, it is atmospheric pressure here, P naught plus H rho G. Pressure here is atmospheric pressure P naught plus H rho G. It is P naught plus H rho G. Now I use my mouth and suck air out of this. When I suck air out of this part becomes a vacuum. That means the pressure here goes to 0. This part becomes a vacuum and pressure here goes to 0. Now there's a higher pressure here and a lower pressure here. So from high pressure to low pressure, a force will appear and it will create a force on the liquid in that direction. Okay? So now in this side of the straw, it is atmospheric pressure plus H rho G. In this side, it's a vacuum, no pressure. So due to this pressure difference, the liquid will be pushed in this direction. Clear? Due to this pressure difference, liquid will be pushed in that direction. So the liquid will flow in that direction. Clear? That's the behavior of the pressure behavior of a straw. Clear? Okay. Okay, let's move forward. Let's move forward. There are other applications of this pressure too. Okay, there are other applications of this pressure. What are they? Actually, things float due to this pressure. Okay, that means if you put something into a liquid, okay, if you put something into a liquid, okay, it actually floats. It actually floats due to this pressure. Okay, due to this pressure. Okay, because the liquid creates a certain pressure, and all these pressure forces together balance the weight. Okay, all these pressure forces together balance the weight. Okay, so that's what actually happens. Okay, so things floating is actually a result of pressure. Okay, but we give a separate name for this. We give a special name for this. මෙයාට අපි විශේෂ නමක් කියලා මොකක්ද? upthrust උඩුකුරු තෙරපුම. We give a special name for this, which is upthrust. Here we call this upthrust. Okay, so this is upthrust. Okay, so now there's a special law, a specific law that talks about this upthrust. What is that law? What is the name of that law? There's a specific law that talks about this upthrust. What is the name of that law? Mention in the chat. Yes, it's Archimedes. Yes, it's Archimedes. What is Archimedes' law? Archimedes tells the same law in a different way. He tells that if you put a certain object into a liquid, that object will upthrust a certain that object will displace a certain volume, right? That means if you put an object like this, what happens is it will displace a certain volume like this. Clear? It will displace a certain volume like this. Clear? It will displace a certain volume like this. So this volume of liquid, Archimedes said, the upthrust appearing on the object is equal to the weight of this liquid volume. He said that it's equal to the weight of this liquid volume. That means if this volume is V, I multiply it by density rho, which gives the mass into G. This gives me the weight of the displaced volume, right? Displaced volume of the liquid. That means if an object displaced a certain volume of liquid, okay, if an object displaces a certain volume of liquid, that weight of that displaced liquid, clear? Weight of that displaced liquid is equal to the upthrust, clear? Weight of that displaced liquid is equal to the upthrust, clear? That's the definition of upthrust, clear? That's the definition of upthrust. That's how upthrust works, clear? So, got the idea? Got the idea? So there are multiple experiments that we can use to prove this, okay? Like if they ask you a very simple experiment, you can do something like this. You can use a container like this and put a small, like there are some containers like this, okay? There are some containers like this. We call them overflow containers or overflow beakers or overflow tubes. What happens is if any liquid overflows, they comes out of this and falls into another beaker or something like that, okay? So what you can do is you can use a spring balance. So using a spring balance, what you first do is you just hang hang an object on it using it. Okay. So assume that now the balance shows 100 newtons. Now the balance shows 100 newtons. Now you put it into a liquid. When you put it into a liquid, if it shows 80, what is the reason for this difference of 20? Why did it went from 100 to 80? Why did it went from 100 to 80? Who created that 20 Newton difference? Who created that 20 Newton difference? That 20 Newton difference was created by the upthrust. This one fails a certain upthrust by the liquid, and that upthrust giving a force up reduces the reading of the Newton balance or the spring balance. Now, when you put this object into this, some water will overflow definitely, right? Some water will overflow definitely. And you can, using a electronic balance, you can measure the weight of this liquid. Now using this, we can prove that the weight of this displaced liquid is also 20 newtons. By this, we can prove the Archimedes law, which mentions that the upthrust appearing on an object, clear? The upthrust appearing on an object is equal to the weight of the displaced volume out of it, clear? Upthrust appearing on an object is equal to the weight of the displaced volume is equal to the weight of the displaced volume in that scenario, clear? That's how it works, okay? That's how it works, clear? So there are experiments like that, okay? There are experiments like that, and there is a relationship like this, okay? There is a relationship like this. If the upthrust can balance the weight, the object will float. That means if the upthrust is strong enough to balance the weight, the object will float. Okay. If the upthrust is just equal to the weight, that means, assume you put a, if you put a certain object into the liquid, you somehow press it into the liquid. Now, if the upthrust is larger than the weight, this will go up and it will float. Clear? When you press this into a liquid, okay? Now if the upthrust is larger than the weight, it will go up and it will float. And if the upthrust in this scenario is just equal to the weight, that means upthrust is just balancing the weight. If the upthrust is just equal to the weight, it will just stay there under equilibrium. Why? This is equilibrium under two forces, weight and upthrust. If these two are entirely equal, clear? If these two are entirely equal, no resultant force on the object, right? Clear? If these two are entirely equal, there is no resultant force on the system, clear? There is no resultant force on the system, so the system will stay stationary, clear? So if under this scenario, if the upthrust is entirely equal to the weight, okay, the object will stay there, okay? The object will stay there, okay? It will be stationary, okay? And object will float inside the liquid, okay? And if the upthrust is not strong enough to hold the weight of the object, that means if the weight is too much, okay? If the weight is too much, this will sink down. Assume about a metal particle. You put a metal particle, loha kallak damma. If you put a metal particle, what happens? If its weight is too much, it will sink to the bottom, right? It will sink to the bottom. So that decides whether something floats inside the liquid or whether something sinks, okay? Clear? That is the story. So what happens when a boat sinks? What happens to Titanic? A collision created a small hole in it. Then water starts coming inside. When water comes inside, water fills into this, its weight increases. After a certain point, when it is filled with water, its weight is too much, the upthrust can't balance it, so it sinks to the bottom. Clear? That is the mechanism. That's how a boat goes down. That's how a boat sinks in. Clear? Got the idea? So that is about hydrostatic pressure and floating, and we use this mechanism to measure density. Okay, we use this mechanism to measure density. We call them hydrometers. Okay, we call them hydrometers. That means based on the density of the liquid. Okay, based on the density of the liquid, if you put a system like this, it will sink to a certain level. If the density of the liquid is too high, that means a very strong liquid, this won't sink much. But if the density is too low, this will sink a lot. So this mechanism we can use to measure the density. Clear? This mechanism we can use to measure the density. Clear? So we just mark the density values on this. Okay, we just mark the density values on this. So lower densities would be up here. Why? In lower densities it goes down, it sinks down. So lower densities are marked up here, but higher densities are marked down here. Why? In higher densities this may come up. Clear? In higher densities this may come up. So higher densities are marked here, lower densities are marked here. Clear? Higher densities are marked in this area, lower densities are marked in this area. Clear? That's how the density is measured using a hydrometer. Clear? Clear? Ah. Okay. Got the idea? Okay. So someone has asked to explain this one a bit. So this concept is hydrometer concept. Okay. So what actually happens is, as you saw here, if the weight of the object is too much, that means compared to the density of the liquid, if the weight of the object is too much, it will sink. Compared to the density of the liquid, if the object's weight is low, it will float up. So this mechanism we can use to measure density, right? In lower densities, this will go down, it will sink. In very high densities, it will go up. So based on the height it goes, okay, we can use it to measure density. So we can mark the density values here. Clear? We can mark the density values here. Clear? In lower densities, it will sink down. So we can mark low densities in this area. In higher densities, it will go up. So we can mark higher densities in this area. Clear? Got the idea? Yeah. It tries to stay straight. Okay. We use some other mechanisms to keep it straight. Okay. there are some requested to do some questions too. So I'm actually planning to do a whole question session, okay, covering a lot of areas, most probably on Monday evening. I'll let you know. I'm planning to do a whole question session, like most probably trying to do all the questions in your tute, going through questions here and there, like a very quick revision, like a question based revision I'm planning to do on Monday, okay. I'll let you know about that, okay. It will be a question based revision. That means using questions, I'll revise the content again and again. So the questions will happen, okay. The questions will happen, I'll let you know, okay. So moving forward, okay, any other questions, anyone? Okay, sure. We'll properly decide which questions to do, okay. Clear. So let's move forward. Someone has asked the siphon concept. It's a similar thing, okay. It's the same thing, okay. Why? See, in a siphon, what happens is, okay, you can learn better. Siphon concept, you can learn better in A levels, okay. In A levels, we have something called the Bernoulli's principle. That's the actual thing that decides the siphon concept. But here, we can use something like this to explain it. Now, see, when I put something like this, okay, here it is atmospheric pressure everywhere, okay. In atmosphere, everywhere you have the atmospheric pressure, okay. Atmospheric pressure, everywhere you have the same atmospheric pressure. So it's the same atmospheric pressure here, and it's the same atmospheric pressure here, okay. Focus. It's the same atmospheric pressure here, and it's the same atmospheric pressure here, okay. Now what would be the pressure here? What would be the pressure here? The pressure here is the atmospheric pressure. And what is this height? If this height is h, what would be the pressure here? It will be P naught plus H rho g, right? It will be P naught plus H rho g. Clear? The pressure here would be P naught plus H rho g. So this point has a higher pressure as P naught plus H rho g. This point has a lower pressure as P naught. Clear? This point is P naught plus the H rho g. This is just P naught. Clear? So there's a pressure difference between here and here, right? And this one has a higher pressure. We know always liquid flow from higher pressure to lower pressure, right? Okay. Even gas, when you open a balloon, that's why air goes out. Why? There's a higher pressure inside the balloon and air pushes out. Okay. So here also there's a higher pressure here and a lower pressure here. Due to this pressure difference, the water will be pushed through the tube. Okay. Water will be pushed through the tube until they comes out of here. Clear? Water will be pushed out of the tube by the pressure difference felt at these 2 points. Clear? Using the pressure difference felt at these 2 points, water will be pushed out. This is not the actual way it happens. The actual way it happens uses Bernoulli, which is not in your O-level syllabus. Okay, it's in your A-level syllabus. So, is it clear? Is it clear, the student who asked this, the siphon concept? Okay, that's how it works. Clear? So rough explanations would be enough for your paper. Okay, just explain what is happening. There's a pressure difference. The pressure difference will push the liquid and the liquid will flow in that direction. Clear? Clear? That's how it works. Okay, that's how it works. Okay, that is the concept of siphon. P naught is atmospheric pressure. That's the symbol I use for atmospheric pressure. The pressure we have everywhere around us. So it's the same pressure here because this point is connected with the atmosphere. So it is here also it's atmosphere. Here also it's atmosphere. Here also it's atmosphere. Everywhere it's atmosphere. So everywhere you have the same atmospheric pressure. So here also it's atmospheric pressure. Why? It's connected with the atmosphere. Here also it's atmospheric pressure because it's open to the atmosphere. Any point which is in contact with atmosphere would have the atmospheric pressure. So here also you have the atmospheric pressure. Here also you have the atmospheric pressure. So if this is atmospheric pressure, here it is atmospheric pressure plus the additional hydrostatic pressure, which means P naught plus H rho G. Clear? Atmospheric pressure plus the additional hydrostatic pressure. P naught plus H rho G. Here it's just P naught. It's open to the atmosphere. So there's a pressure difference. It will push the liquid in this direction. Clear? So P naught is the atmospheric pressure, the pressure we have around us everywhere. Clear? The pressure we have around us everywhere. Okay. So that is the mechanism. Next. Next. I'll do a quick overview of work power energy too. Okay. I'll do a quick overview of work power energy too. I'll do it quickly but in a much practical way. Okay. In a much practical way. So we know that work means if you push something, you are doing a work, right? If an engine moves a vehicle, engine is doing a work. Yeah. Like that, whenever there's a force and a motion due to force, there's a work done, right? Work done means something useful is happening, right? Work done means something useful is happening. So whenever there is a force and a motion due to that force, clear? Whenever there is a force and a motion due to that force, a work happens, clear? Whenever there's a force and a motion due to that force, a work happens. So work equals Fx. Work equals Fx. Clear? Force into displacement. Clear? Force into displacement. That is work. Clear? That is work. Okay. So how do we write the work done? If there is a force and if there is a displacement happening due to that force, we tell that there is a work. Okay. That there is a work. Okay. So work done can be written by force into displacement Fx. Clear? Okay. So and what is the result of a work? What is the result of a work? In our syllabus, we can talk about two results of a work. What is that? One is kinetic energy. That means things get a velocity due to work. That means now this guy is stationary. I keep applying a force on this guy. I keep applying a force on this guy. Clear? Now there's a force. I keep applying a force on this guy. What happens? It accelerates. It accelerates. That means it's gaining a velocity. Clear? It's gaining a velocity. Clear? Okay. So if you are applying a force and there is a displacement, what is the result? It gains a velocity or a motion. So some objects gain a motion due to a work done on it. We call it an energy, and we give the specific name of kinetic energy to them, and the kinetic energy is written as half mv squared. That means if you take an object and provide a certain force on it until a certain distance, the work done by you on that object will be converted into its kinetic energy. Work done by you will be converted into its kinetic energy. Here. For an example, if there's a question like this, okay, you are applying a force on an object, a force of 10 newtons, and by 10 newtons you are moving it a distance of 10 meters. If the mass of this object is 5 kilograms, what would be the velocity of the object here? So what is the answer? Now you are doing a certain work. What is the work done by you? It is Fx. It is Fx, which means 10 newtons. Force is 10 newtons and the distance is 10. Clear? force is 10 newtons and the distance is 10, clear? Fx, which means 100 joules. Work, energy and everything is measured by joules, okay? Work, energy and everything is measured by joules. Now this work done by you on this guy, what is the result of that? It creates a kinetic energy on this object, clear? It creates a kinetic energy on this object. So the same work done turns into the kinetic energy of the object, which is half mv squared, which is half, what is the mass of the object? As I mentioned, 5 kilograms v squared. And this work done, which is 100 joules, is equal to half 5 v squared. Half 5 v squared. Now you just have to solve this and get the velocity of value of velocity. So what is v squared? So in this case, what is v squared? V squared equals 100 into 2, 200. 200 divided by 5. What is 200 divided by 5? What is 200 divided by 5? It becomes 40, right? It becomes 40. So v squared is equal to 40. Then v is square root 40. Then v is square root 40 meters per second. Clear? V is square root 40 meters per second. That's how it functions. Clear? V is square root 40 meters per second. Okay. See, work done. One specific use case of work done is gaining kinetic energy. And another type of energy that we can obtain by doing a work is potential energy. Potential energy means instead of accelerating, you provide a change in position to an object. That means you move it up. That means you move something up. Clear? You move something up. This is another way of doing a work. Instead of accelerating, you change the position. You change the position. So how can you write the work done when changing the position? If the weight of the object, I mean this proof is actually not required. So let's go like this. So if you are applying a force of F to a distance of x, the work done by you would be Fx. Work done by you would be Fx. So if you change the position by a height h, work done would be Fh. Fh. And here the work done by you is converted into the potential energy of the system, and we write it using mgh. H is the height of the object lifted, g is the gravitational acceleration, m is the mass. Here m is the mass. So sometimes the work done by you converts into the potential energy of an object. Clear? It converts into the potential energy of an object. Clear? So there are two scenarios. Sometimes work done turns into kinetic energy. Sometimes work done into potential energy. Sometimes potential energy turns into kinetic energy and kinetic energy turns into potential energy. What is an example? Think if you place something like this and release it. You place something like this and release it, what happens? What happens? When it moves down, its height from earth decreases, right? Its height from earth decreases. When it moves down, its height from earth decreases. So its potential energy decreases. What happens to this potential energy? It turns into kinetic energy. So the velocity of this object increases. Clear? It turns into kinetic energy. So its velocity increases. That's why when you release something like this, it falls down. So its potential energy decreases, but that potential energy converts into kinetic energy. There's a rule in the world: energy cannot be discovered or energy cannot be destroyed. All you could do is converting energy. So now when I'm walking, what is happening? When I'm walking, what is happening? I absorbed some chemical energy from food, right? I absorb some chemical energy from food. That chemical energy turns into my kinetic energy. That's why I'm gaining a velocity, right? Okay, that's why I'm gaining a velocity. That chemical energy converts into kinetic energy. When I jump up, my chemical energy I obtain from food turns into my potential energy when I jump up. What happens in solar panels? In solar panels, the energy, the heat energy we receive from sun turns into electrical energy. What happens in a diesel engine? The chemical energy in diesel converts into the kinetic energy of the vehicle. What happens in a petrol engine? The chemical energy of petrol turns into the kinetic energy of the vehicle. Like this, it's all energy conversions happening in the world, right? All energy conversion. So if the potential energy decreases, it cannot be destroyed. Okay, if the potential energy decreases, it cannot be destroyed. It is just converted into kinetic energy. Clear? It's just converted into kinetic energy. If I show you a small example, okay, if I show you a small example, think about this. Think about this. You place an object like this. Mass is 5 kilograms, G is 10. If it falls a distance of 5 meters, its potential energy decreases. Its potential energy goes down by mgh. What is the value? Mass is 5 kilograms, G is 10. It goes down by 5 meters. Mass is 5 kilograms, mass is 5 kilograms, G is 10. It goes down by 5 meters. So the energy, potential energy loss is 5 into 5, 25 into 10, 250 joules. That means when we go down, potential energy goes down by 250 joules. But what happens to this? It turns into the kinetic energy of the object. That's why if I release something like this, it accelerates downwards. Why? The potential energy we are losing, converts into the kinetic energy. So what is the kinetic energy that we gain? The kinetic energy that we gain is half mv squared, right? Kinetic energy that we gain is half mv squared, which is half. What is the mass of the object? It is 5 kilograms v squared. Then here you have 250. The potential energy we lost turns into kinetic energy. Clear? The potential energy we lost turns into kinetic energy. That's how it happens. You solve this, you get the velocity. So what is the value? What is the answer? 250 equals half 5v squared. So v squared equals 250. You take this 2 into this side, so multiply by 2. You take this 5 down, so divided by 5. So you get 250 into 2 is 500. 250 into 2 is 500 divided by 5, which is 100. So v squared equals 100. And what is 100? 100 is 10 squared. 100 is 10 squared. Then v becomes 10 here. So it's not energy losses, it's actually energy conversions always. Clear? It's never energy losses, it's actually energy conversions. Work done by you turns into kinetic energy or potential energy. Potential energy turns into kinetic energy. Kinetic energy turns into potential energy. Mechanical energy turns into chemical energy. Chemical energy turning into electricity. So it's never energy losses or energy gains. It's just energy conversions. There's a universal truth that energy cannot be destroyed or energy cannot be invented. It should be just converted from one type of energy to other types of energy. Is clear? It should always be converted only. Clear? Energy is just conversions. Clear? Energy is just conversions. Clear? That's the story. Okay? That's the story. Is it clear, everyone? Is it clear? Put in the Zoom chat and in the YouTube live chat. And if you need to know anything to get tunes to join the groups, and we created a new channel so that you can get tunes and all the resources by one place too. So for anything like that, contact our hotline. Okay, 070 154 6825. 070 154 6825. Clear? 070 154 6825. Okay, so there's a question: what is the energy conversion of immersion heater? It's simple. Why? Immersion heater gets electrical energy from our plug, then it turns it into heat. So it gets electrical energy and converts it into heat. So it's electrical energy into heat. Okay, it's electrical energy converted into heat. Like that, you should be able to figure out energy conversions in different scenarios. Okay, we'll learn more physics if you decide to do biomaths for A levels. Okay, there's a lot of physics out there. So okay, I mean here what happened was I just drop it, then it falls down. So when it falls down, it loses its potential energy. When you go up, your potential energy increases. When you go down, your potential energy decreases. So this is how much of a potential energy you lost. You never lose potential energy. What actually happens is when you fall down, your level goes down, so your potential energy decreases, but your kinetic energy increases. You are accelerating. Clear? That means your velocity increases. Okay, that's the conversion happened here. Clear? So let's meet again in 1 hour. Okay, we have optics and waves. We are ready for with a bunch of demonstrations too. Okay, we'll show you how it actually happens, how it actually works, and you can you should try and understand and try to figure out what actually happens in waves and optics. It will be quite beneficial. Okay, so that session is happening within 1 hour, as I remember, at 7. So let's meet at 7 again, and all the resources and tunes and everything will be available in the group. Okay, so thank you everyone.